I'll repeat myself for those of you watching on YouTube, because some students are watching from wherever. The law of conservation, of energy. It should be dramatic. Thunder should rumble, lightning should flash. This is one of the fundamental laws of the universe. This explains an awful lot why you can't do certain things, why we can't have a perpetual motion machine, why you can't get energy from nowhere. What does it say? It says, I'm going to give it to you first of all, kind of technically. The total energy of a closed system is neither increased or decreased in any process. The energy you start with will always equal the energy that you finish with. Or the energy's got to come from somewhere. If you've ended up with some energy, you better figure out where that energy came from. It can't come from nowhere. And if you think it came from nowhere, you're making up a nonsense machine that will not work. Energy can be transformed from one form to another. You can change potential energy into kinetic, into electric energy, into heat, into sound. But the total will remain constant. I wrote here, Mr. Dewick has a good demo for this. I'll show you that in just a second. According to the work energy theorem, if we have a closed system with no outside sources of energy, what do I mean by this? You're not plugging something into a wall where there's outside sources of energy, or you're not adding an engine or gasoline to the system. If we have a closed system with no outside sources of energy, you get no extra or useful work. Whatever work was set up at the beginning for that system, that's all you got. So, what was the work energy theorem from your formula sheet? Wes, can you read it to me? Don't tell me force times distance. Read me the one that has work and energy in it. Good. The law of conservation of energy, Aidan says, okay, if you don't bring in an outsider to push, or if you don't bring in an extension cord and plug it in, or if you don't bring in a motor and some fuel as an extra energy, so if you have a closed system, you get no useful work. You don't get anything extra out. Remember when I held the bowling ball over your head and I raised it higher? Okay, the only way that was able to happen, I had to give it some of my energy. There is no way in the universe that that bowling ball on its own will spontaneously gain that energy. By the way, we've just explained why telekinesis is not a thing. You can't move objects with your mind without touching them. I'm sorry, no matter how hard you concentrate. And I'm going to make the assumption that most of you, at least once when you were a kid, tried staring at something as hard as you could and tried moving it with your mind as hard as you could, and you tried, and I'm sorry, you cannot. What's changing anything? By the way, it's amazing how many of you, I could tell you were smiling behind your mask when I just said that, because you're going, I thought I was the only one that tried that. No. Okay. What's changing anything? So this is really PE final minus PE initial plus KE final minus, Mr. Duke, KE initial. Change in plus change in. Is that okay, Karn? I agree. I don't like the way that's written right now. See the minus sign in front of the PE initial? And see the minus sign in front of the KE initial? I'm going to plus them both over to the other side, especially because the other side right now has a 0, Noah. I'm going to get this. KE initial plus PE initial equals KE final plus PE final. The amount of energy you start with will always equal the amount of energy you finish with. This is the law of conservation of energy. And it's the last one that I gave you in this unit on your formula sheet, I think. I gave it to you. Oh, no, it's not the very last one. I'm probably going to skip efficiency this year because I got to cut corners, but you definitely have KEI plus PEI equals KEF plus PEF. Yes? Okay. Now, That's in our magic physics world where everything works out really nice. And this alludes to a conversation Sean and I were having yesterday. Sean was asking me about momentum, and he said, well, momentum is conserved and energy is conserved. What's the big difference here? Because there's so many different forms of energy, we're going to be sloppy. If we want to include, most of the time you're losing energy to heat and to friction. So for example, this bulb, this projector that you see in front of you, it's not very energy efficient, because if I put my hand here, there's a lot of heat. In fact, one time I blocked this bulb off with a styrofoam cup because I didn't want kids to see the screen, and it melted the styrofoam cup. There's a lot of heat coming from that bulb. Terribly inefficient. Most of the time, energy isn't perfectly conserved because we're losing to heat. It is conserved if you add up the heat. So if we want to include friction, we get a modified version. KE initial plus PE initial equals KE final plus PE final. Whatever's missing, if the numbers don't match, plus heat, it must have all gone into heat. Pause the video for just a second. A great example of a conservation of energy system is a skate ramp. So what I'm going to do is I'm going to lift this skater up. What I'm really doing is I'm giving them potential energy. Are they moving right now? How much kinetic energy do they have right now exactly as a number then? What's all of their energy right now? Potential, mgh. When I let go, what's going to happen? That potential energy is going to turn into kinetic energy, and then back into potential, and back into kinetic, and back into potential, and back into kinetic. Now, right now, I have friction turned off, but can I do the bar graph, Mr. Dewick? This one doesn't have the bar graph. Oh, graphs. There we go. Here we go. Same idea. Okay? Go. You know what? I'm going to pause for a second. I think I like the story again for those of you watching at home. So give them potential energy, turns into kinetic, turns into potential, turns into kinetic. In fact, here's what's going on. Can you see the total energy is not changing? That's the law of conservation of energy. What's really happening is at the top, all of the energy is potential energy. None of it's kinetic. If none of it's kinetic, what's our speed? Got to be, because I have mv squared. M isn't zero. V must be zero. That's the only way KE can be zero. What about at the bottom? Our potential energy is zero, or it would be if I'd managed to stop it just right. That's when you're your maximum. That we've just explained why you go the fastest at the bottom of a ramp, or a swing is another great example of this, and why you're at your slowest and then stopped for a split second at the top. Is that okay? Now, right now, we're ignoring friction. I can even do a little pie chart right here. Okay. Right now, we're ignoring friction. I'm going to turn friction on. This is much more accurate. I've got a little bit of friction. Is the total energy changing? The gold bar, is that changing at all? But can you see where is more of our energy being bled off into? Heat. We're losing energy to heat. Not going away, but this is why in real life, air resistance and heat, we're lumping that all together. You would end up slowing down. This is why in real life on a skate ramp, you've got to add some extra energy each time from your body through your legs, okay? But we can be a bit more accurate. So this is the law of conservation of energy. Where is all the energy eventually going to get turned into? What type of energy is it all eventually going to get turned into? Thermal, heat. That's the story of the universe. Sorry to break it to you, but the universe, a few billion, might be more than a few billion, I got to run the numbers, years from now, eventually, Earth right now is very, very much mathematically like this skateboarder here. We're a huge bundle of energy right here in our area. But that energy is slowly being radiated out as heat. Eventually, the entire universe will end up like that with an average temperature of about 4 degrees Kelvin. Okay? all of the heat in all of the stars, all those bundles of energy in the universe, over a few 100 billion years is going to spread out, and eventually it's not going to vanish, but there's really not very much energy in the universe when you compare that to the total volume of the universe. Newsflash, you're going to die someday, as is the universe. Sorry to break it to you. Is that all right? That's the law of conservation. What was that? Well, let's make a prediction. What would happen if there's way more friction? It'll come to a stop way quicker. You know what that's like? You haven't oiled your skateboard wheels. Lots of friction. What you're going to find is a lot of your energy is going into heating up the axles of the skateboard wheels. So you ready? And here the friction would be heating up the skateboard, and friction between, actually most would be going up into heating up the skateboard wheels. Okay. You may have noticed it if you ever try and do a really quick stop on your brakes on your bike. Touch the brake pads really quickly. If you've done a massive stop, they're warm, very much so, because the energy had to go somewhere. And typically, especially for cars hitting the brakes and for bikes hitting the brakes, it's almost all going into heat. It's one of the reasons electric cars are so much more efficient. Anybody here have an electric car that has regenerative braking? Okay. Those, to stop, you're not actually using the brake pads to stop. You're bleeding the energy off, the kinetic energy, and you're turning it cleverly back into electric energy. But because the car is losing kinetic energy, it has to slow down. But that extra energy isn't going into heat. Some of it still is. Most of it's going back into the battery. That's why they're so much more efficient. How does that work? I wish I could teach. We would have got to it at the end of the year when we looked at electric motors, but we're not going to get to it this year. Okay, so that's the energy skate part demo. Mr. Dewick has a good demo for this. I got to pause the video. Example 1, let's start doing some physics. A projectile is launched straight up into the air. If it reaches a final height of 93 meters, what was its initial velocity? Use energy to solve this. Now, we could totally, don't write this down, we could totally solve this by going VI equals question mark, D equals 93, A equals negative 9 point. We could totally do it that way. But I want you to know that we could also use the law of conservation of energy, G. So let's write down KE initial plus PE initial equals KE final plus PE final. And maybe at the top of the page, because this is brand new to you, in previous years you would have memorized these because I would have flogged them so much. You might want to write down that KE equals a half mv squared, and that gravitational potential energy, PE, is mgh. Might want to jot that. That's on your sheet, too. And then once I've written down the law of conservation of energy, I always pause and I ask, are any of these zero? Now, for potential energy to be zero, really what we mean is the height zero? Am I ever on the ground? In this question, are we ever on the ground? Where? Initial or final? Of course, PEI is zero. It's not a real province, right? Oh, come on. They call themselves the premier. You're the mayor of PEI. You're not a premier. Come on. It's an island. Now, how can KE be zero if V is zero? Is there ever a point, if we're imagining this launch into the air, where the object is at rest? Is that final or initial KE? Okay. So we have this, a half mv initial squared equals mgh final. Now, I'm sensing the vibe. I'm sensing right now, many of you have been so focused on your forces test that you haven't done the work, lesson 1 homework yet. So tune your brain in, because you're going to be learning stuff a little more from scratch than I'd like. Is there an M in everything? Yay. What do they want me to find? How would I get the VI by itself? I can either divide by 0.5. I'm going to times by 2. Because if I go times by 2, that cancels. And I'd rather times by 2 than divide by 0.5. And then that gives me a VI squared. Hello? Gives me a VI squared. I get VI equals the square root of 2GH. Final. Put your pencils down, look up. If we had done this with Physics 11 kinematics, we would have ended up going VF squared equals VI squared plus 2G, or sorry, plus 2AD. What was VI? Oh, sorry, no. What was VF? We would minus the VI over, and we would go 2AD. How to get rid of that? Can you see these are sort of the same equation? Okay? There's technically a negative here. Really what I would do is I would have minused this over, but since A is negative and that's negative, there's a negative times a negative, which is a positive. So we could have solved this with Physics 11 kinematics. But anyways, I just wanted to show you that conservation of energy doesn't break any of our understood laws of physics. It fits in. 2 times 9.8, not negative because we're in Scalarville, times 93. What do you get? Kind of have to get your calculators out. $46.7? 42.7? Gotta be honest, Aiden, I would never solve example 1 with energy. I would go VI equals question mark, VF equals 0, A equals negative 9.8, D equals, we're above positive 93. I'd get the VI by itself. So I wrote here, we could use kinematics to solve the above question, but the law of C of E, conservation of energy, really shines, and this is going to be your phrase for this unit. If your phrase for last unit was, is there more than one, this is a job for a free body diagram? If your phrase in the previous unit was, is there angles, components? Your phrase for this unit, if there's a change in height, a change in speed, and especially if there is a yucky, curvy path, or if the question mentions heat, that's a job for conservation of energy. In other words, roller coasters, baby. I guarantee your work energy test is going to have a roller coaster. Oh, heck, I'll even tell it's going to have 2 roller coasters. It might even have 3 roller coasters to analyze, because I'm nuts about roller coasters. I love roller coasters. So let's analyze a roller coaster. A 350 kilogram roller coaster car is traveling at 22 meters per second. If the car starts out at a height of 12 meters, how fast will it be going when it gets to ground level? Ignore friction. I'm going to dulp. So we have something, I guess, kind of like this. There's our roller coaster. And right here, there's our car. How fast are we going right there, according to this question? Sorry? No. 22. Final is going to be here. Oh, and it tells me that we are 12 meters above the ground. Now, here's the beauty. This will work, Karn, if the coaster does this. Different path. This will work if the coaster does this, or if the coaster does this. All scalar conservation of energy cares about is where'd you start, where'd you end up. Doesn't care about what happened in between. If we tried to solve this using forces and kinematics, we would have to take into account each one of these changing angles. It would be a nightmare. I'd use a software computer to do it. No, I wouldn't. I just wouldn't even bother. I'd use conservation of energy. So you ready? See my doll? Hopefully you've drawn a little picture. Is there a change in height? Is there going to be a change in speed? In fact, I think at the bottom of the hill, are you going to be going faster or slower? Okay, so is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. KE initial plus PE initial equals KE final plus PE final. If the question had said, oh, and include friction, don't write this down, I would also add plus heat. But did the question say include friction? No heat. Are any of these zero? Let's look at potential energy first. Are we ever at a height of zero? Really? Yawning twice now? What was that? Can you use, final? Yeah. I agree. Are we ever at a speed of zero? Did we start at rest? By the way, if I had started at rest, then I could cross out KE initial. And you know, when you're coming over that first hill, you're close in a real roller coaster, you're close enough to rest that often we'll treat it that way. But this must be like the second or third hill that we've gone up and we've already got some speed. So is anything else zero? I don't think so. I don't think we're at rest anywhere. So now let's expand the KE and the PE. That's going to be a half m v initial squared plus m g h initial equals a half m v final squared. Oh! Ha! Karn, is there an m in the first term? Is there an m in the second term? Is there an m in the third term? Is there an m in everything? What's that mean? How many of you have been on a roller coaster before? How many of you, before you got on the roller coaster, you had to stand on a scale and they had to measure your mass and make sure that they spread the mass all out evenly and they didn't put heavy people next to other heavy people, that they made sure they spread it all? Any of you do that? Do you know why? M's cancel. Or, how many of you have ever seen an empty roller coaster make it through the track as well as a full roller coaster make it through the track? You know why? M's cancel. It's the only reason that works. Okay. Or, can little kids and grown-ups go on this ride? Yes. Why? M's cancel. Kind of nice. So even though I said a 350 kilogram roller coaster, did I really need to give you that 350? No. What are we trying to find? More specific in my equation right here, what am I trying to get by itself? Okay, I'm going to show you a great trick. Okay, what's right in front of the VI here? A half. What's right in front of the VF here? I'm going to clear fractions. What I'm going to do is I'm going to times this by 2. I'm going to times the GHI by 2 and that by 2 because it's going to make my equation much prettier. Because here, do you know what 2 times a half is? 1. Do you know what 2 times a half is? 1. I'll still have a 2 in front of the GH, but that's way nicer. I get this. VI squared plus 2GHI equals VF squared. Mr. Dueck? Yes, Sean. I'm having a little deja vu here. Are you? Don't write this down. Are you saying that this looks really similar to VI squared plus 2AD equals VF squared from Physics 11? Yes. It's the same concept. We're just expanding on it. I got VF squared. Anybody? So VF is going to be the square root of, I've scrolled down. What was VI? 22 squared plus 2 times 9.8, not negative, we're in Scalarville. Height was 12, I think. How fast are we going at the bottom of the hill? 26.8? Anybody else? Could you multiply it by 3.6? How fast is that in kilometers per hour? I'm going on this coaster. That's a good coaster. I'm in, baby. What was it, 26.8? Okay. That's a pretty good coaster. I'll take that. Conservation of energy lets us analyze roller coasters. Example 3. Turn the page. An object is dropped from a height of 40 meters and it strikes the ground with a speed of 25 meters per second. How much heat energy was produced during the fall? Nick, what's this question asking me to find? How much what? Yeah. Is there a change in height? Is there going to be a change in speed as it falls? There isn't a yucky curvy path, but are they asking about heat? This is a job for conservation of energy, but I'm going to add heat to the equation. So I'm going to say this. Kinetic initial plus potential initial equals kinetic final plus potential final. And if the numbers don't add up, it's because whatever's missing went into heat. Heating up the air and heating up the ground on impact. Really, Mr. Duick? That much heat? Yeah. Put your pencils down. Back here. Are any of these zero? Potential energy is the energy of height, MGH. Is our height ever zero? Initial or final? Oh, PEI gets to stick around for a change. Okay, final. Kinetic energy is the energy of motion, of speed. Is our speed ever zero? What did dropped mean last year? Instead of start, can we use a physicsy term? Maybe that starts with the letter I. Thank you. Start. The end. So we have this. MGH initial equals a half mv final squared plus heat. Allie, is there an m in the first term? Is there an m in the second term? Is there an m in the heat? No. Do the m's cancel this time? No. Nope. What are we trying to find? How would you get the heat by itself? How would we move that half mv squared over? Loud and proud. What? You're right. Someone said it here. Loud and proud. Minus. Say it again. And the reason I'm emphasizing it, I don't know why. This question here, this one, this specific situation, for some reason, I see kids divide by a half mv squared, and I haven't figured out why on earth they would. I mean, there's a plus sign. To me, it's pretty obvious, but this seems to be one of those silly mistakes. In fact, if we only got 16 in this class this quarter, next quarter, I have 2 physics 12s. I'll guarantee you at least one kid will do that on the test. Happens every time. I don't know why. It's just bizarre to me. So yes, I agree with you, Karn. It's going to end up being MGH initial minus 0.5 MV final squared. I made the 1/2 of 0.5 because I'm going to my calculator soon. That equals heat. Karn, do you mind? Can I put the heat over on this side where we're used to seeing it by itself? We've done that before. All right, plug and chug. Heat equals M 18, G 9.8, 40 minus 0.5, 18, 25 squared. You better get a positive answer. If you got a negative answer, that would mean we were losing heat and somehow getting energy from nowhere. I don't think that's happening. Typically, answers in the joules are in the thousands or tens of thousands, I suspect. And you should be able to type that in one line, I hope. Nick, what'd you get? 1,000? 1431. Anybody else? 1431? So I'll go 1430 to 3 sig figs, but if you want to, you can write 1431. It's funny, you can't tell as I'm teaching. So many of you are just fidgeting with the heat packs. Oh, so warm. It's weird. Those haven't caught on in North America. In Europe, when I have international students, especially from Germany, they're all, oh yeah, I must do it. You've seen that before. They use them all the time because they're a reusable, environmentally friendly heat pack. In North America, we have such a disposable society. We want the ones that you crack and use once and throw in the trash, I guess. I don't know. Dumb. Example 4. What's example 4 asking me to find? How much what? Oh. How much what? This is not a job for conservation of energy. How much what? So my first thought, don't write this down, look up. My first thought would be to go work equals force times distance. Looking at the question, do you see a force? Do you see a distance? I would say, My second thought would be work is the area under a force versus distance graph. Captain Obvious, did they give me a graph? What's my third, more cumbersome but better definition of work? Connor, what's my third, more cumbersome but better definition of work? Look at your formula sheet. Don't look at me stunned. Yes. Yes. Connor, does this question imply a change in height anywhere? A hill anywhere? I'm going to ask you the same question. I want the same answer. I'm just going to phrase the question differently. Is there any change in potential energy? Karin, what's change in anything? So the change in kinetic is going to be a half mv final squared minus a half mv initial squared. There's my final minus initial. I kind of did 2 steps in one. Normally I wrote ke final minus ke initial, and then I brought on the half mv squared. But are you okay if we did it in one step? Are any of these zeros? Is our final velocity 0? Speed, sorry, 0. Hello? Is our final speed 0? No. Is our initial speed 0? What don't I like about the speeds, by the way? Yeah, okay, kilometers per hour. Oh, how would I convert that to meters per second? There was a gimmick, something to do with the 3.6. Is it divide by 3? Okay, so you ready? Work is going to be 0.5. Oh, is there an m in the last term? Is there an m in the middle term? Is there an m in the w? No, mass doesn't cancel here. It takes more work to stop a semi than it does to stop a smart car. Yeah, that makes sense to me. So 0.5 times 1200. I'm so lazy, I'm going to go 50 over 3.6 squared. I'm just going to do it in the question. Minus 0.5 times 1200 times 80 over 3.6. And we're slowing down. Final is smaller than initial. You're going to get a negative answer. Negative. Okay, how would I type this in? I would go 0.5 times 1200 times bracket 50 divided by 3.6 close bracket squared minus 0.5 times 1200 times bracket 80 divided by 3.6 close bracket squared. Oh, I put the squared in the wrong place. Outside the brackets, Mr. Duke. You get negative 180 and then 5 repeating. So 181,000, negative 181,000. That's how much energy the car has to lose to slow down by 30 kilometers per hour. What force does that work? You know this. What force makes a car slow down or speed up, for that matter? Friction. Okay, the car lost 181,000 joules of energy. That's why it's negative. Also, it's because the car is going forwards, but to slow down, which way is the force acting? Backwards. They're in opposite directions. So, but that energy doesn't vanish. Where'd that energy go? Unless you have a regenerative braking system for an electric vehicle. Then most of that energy went into recharging the batteries. What kind of vehicle do you have, Wes, or do your folks drive? Yep. Okay. How about you, McKenna? Ooh, okay. I've test driven a Tesla. My friend has a Volt. I know in the Tesla, as soon as you take your foot off, they don't call it a gas pedal, they call it a go pedal because there's no gas, but as soon as you take your foot off the accelerator, it feels like you're hitting the brakes.
Yes, I drove one.
Yep.
Because it's my own girlfriend.
Yep.
And we had to turn the setting off because like this was when I had just got
Yep.
my L.
It takes a bit
And
to.
it was like really
Yep.
weird because it felt like it was constantly stopping.
And that's because as soon as you stop feeding electricity through the system, it's actually setting up what's called a back voltage. It's sending up a reverse current and bleeding that from the wheels, recharging the batteries. And that's how you slow down. When I took my Tesla for a test drive, when I took a Tesla for a test drive, one of the things I mentioned to the salesperson is I'm hardly ever hitting the brakes. To come to a stop, I only hit the brakes at the very end to bring myself to a stop for those final 5 kilometers per hour. He said, yeah, we tell people to get your brakes checked every 10 years or so because you're hardly going to use them. Have you noticed that as well? And the Volt, I think, is very similar. Okay.
I know my license.
Yeah, but you've been in the passenger.
Yes.
You don't pay attention. Okay, fine. Okay. By the way, also, a gasoline engine, do they give off a lot of heat? Do they get like red hot? That's all wasted energy. Because where's it coming from? The gasoline. That's why gas motors are so reprehensibly inefficient. Gasoline engine, can you hear them from a long distance away? Sound energy. Electric motors are too quiet. In fact, they're probably going to have to make electric cars artificially noisy so that pedestrians can tell there's an electric car coming towards them. You're going to have to add sound. Put your pencils down. I'm cutting corners here. I'm going to skip example 5. But we are going to do example 6. So here we have 3 projectiles, A, B, and C. They're fired from the same machine on the moon. Why on the moon? We can ignore air resistance. With the same initial velocity. Their paths are labeled A, B, and C. At the 3 points marked location 1, the tops, which one will have the biggest kinetic energy? A, B, C, or all will be equal? And convince me. You know what? We're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Jewell can make fun of me if I don't vote. I'm Noah. Okay. Here we go. So, at the tops, which of those will have the biggest kinetic energy? Who says, Mr. Dewey? A, it's higher. A. Who says, no, B, Mr. Dewey, B, the middle one. Best way to shoot something at a 45-degree angle, B. Says C. Who didn't vote? Which one you going with, Aiden? Coward. Is there a change in height? Look at the picture. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? I bet you conservation of energy is how I might analyze this. So I'm just going to write down the law of conservation of energy, G. Oh, are we starting on the ground? Telling you, PEI is not a real province. I hope none of you are from PEI, and I hope you understand that's just a joke that I make, again, to try and help you remember dumb stuff. Right? Okay. I guess this is sort of, remember the energy skate park that I showed you at the beginning of the lesson? There, all of the potential was turning into kinetic. Here, all of the kinetic is turning into kinetic and potential. Why is C right? Why must C be correct? What has the most, which location, looking at location 1, which projectile, A, B, or C, has the most potential energy at location 1? Why? Higher. It's higher. Which has the least potential energy? Well, if it has the least potential energy, what must that energy still be in the form of? Kinetic. Okay? So using principles of physics, explain your answer. C has least PE, so most KE. Now, if you want to, you could say least PE and then in brackets, smallest height, so most KE. Because the energy's got to come from somewhere, it's got to go somewhere, Aiden. In other words, if you wanted to put numbers in here, don't write this down, look up. Let's suppose we start with a nice round number of 10,000 joules of energy. If you only have used up 2,000 joules for potential, how much kinetic must there be exactly as a number? If you've only used up 2,000 joules, how much kinetic must there be exactly as a number? 8,000. What if you're higher? What if you've used up 4,000 joules of potential energy? Then how much kinetic energy? You got to be going slower because it's not like your mass has changed. Oh, what if we fired it straight up and we used all 10,000 joules of energy for height? How much does it have left for kinetic? We've now explained finally why last year I told you projectiles come to a stop for a split second at the... This is why. I didn't tell you why last year. We just kind of said, yeah, we've noticed that. Okay. Which will have the greatest total energy? A, B, or C? Or all three will be equal? Once again, we're going to vote. Once again, how high hold your hand up is how sure you are of the answer. So at location 1, A. B. Obviously C, because it's got the most kinetic energy. C. Really? All three will be equal? Why? Let's go back at our setup. Where's all the energy coming from according to this question initially? This? What's the equation for kinetic energy? It's on your sheet. A half mv what? So if they're fired with the same initial velocity and they're the same mass, what can you tell me about their initial kinetic energy? If v is the same and m is the same, their kinetic energy is the, and since that's their total energy is the, in other words, if I started out with 10,000 joules of kinetic energy, do you know how much total energy I have right there? 10,000. Do you know how much total energy I have right there? How about right here, it's for impact? 10,000. It's just some of it may have turned into potential or some of it may have turned into kinetic, but I'm telling you, there's still 10,000. So Noah, at which three parts at the end, which projectile will have the greatest total energy? What's the correct answer? There we go. Okay. Oh, if you're looking for an explanation for both of them, they started with the same total energy. If you want, you can put in brackets KE initial. Oh. Don't autocorrect it. KE initial. There we go. And that happened to be their total energy. Is that all right? This is the law of conservation of energy. Energy's got to come from somewhere. It's got to go somewhere. It can't magically appear and disappear. I like example later, Example eight is a nice question. A car is at rest at the top of an incline, 3 meters high and 3 meters long, and it's released and rolls down the hill. Sorry, 3 meters high and 30 meters long. It's released, it rolls down the hill. What's its speed at the bottom of the incline if the average friction force is 200 newtons? We could probably do this with kinematics and winner minus loser and find A and get the obvious one. Ugh, there's a better way. First of all, is there a change in height in this question? Yeah. Are we ending up at the bottom of a hill? Is there a change in speed in this question? Yeah. Is there a yucky curvy path? No. But is there heat? Did they mention friction? Is there heat? This is a job for conservation of energy. So we're going to go with KE initial plus PE initial equals KE final plus PE final plus, there must have been some heat because they talked about friction. Are any of these zero? PE final? That's convenient. Any of the KEs zero? Are we ever stopped? Oh, that's a bonus. So really what we end up with is mgh initial equals a half mv final squared plus heat. What are we trying to find? Okay, boys and girls, how would I get that by itself? I gotta be honest, we're approaching the area where my love for getting things by itself starts to say enough already. Here's what I'm gonna do. I'm gonna minus the heat over, but I'm not gonna get rid of the half m yet. I'm gonna deal with that later. I'm gonna write this as mgh initial minus heat equals 0.5 mv final squared. What I'm going to do now, Cleo, I'm going to solve that as a number, and then once I got that on my calculator as a number, I'll divide by 0.5 m square root. Just not going to do it all in one step. Too cluttered. I could, but this is about my limit of wanting to type stuff in one step to my calculator. Do I know M? Do I? What's the mass in kilograms? Do I know M? No. Can I figure it out? What's that 3,000? What did I actually give you there? Not M, but what? mg. Okay, so can I figure out m? Yes. I'm not even going to bother doing wherever I see an m, I'll just put a 3,000 over 9.8 on my calculator because I'm that lazy. Or better yet, you know what? For mg, what am I going to write right there? I'll just put a 3,000 there. Do I know h? Initial. 3. Do I know heat in joules? That's why this question's a little bit tricky, but I like this question. I like this question. I like this question. So, you ready? You might want to add this to your purple formula sheet in the work section. Another way to think about heat is the work done by friction. And work is what times what? So I guess it's going to be the force of friction times distance. The distance and the force of friction have to be in the same direction. Okay? So on my next line, I'm going to go like this. mgh initial minus force of friction times distance. That is work, that is joules, that is energy, that is heat. Equals 0.5 mv final squared. Let's go through my little checklist. Do I know mg? 3,000. Do I know h? Do I know the force of friction? What if they hadn't given me the force of friction? I don't think I'll do this year, but in previous years, I've given kids a ramp question and they've had to go friction equals what times what? Everybody. I don't know the normal force. Oh, but look. Ooh, mg perpendicular, of course it is. In other words, it was a nice review of what we just finished. I'm not going to pile that on this year. Here's the question. Which distance? The 3 or the 30? Which of those is in the same direction as friction? The 30. Okay? Yeah? Now let's plug and chug. So it's going to end up being 3,000, 3 minus 200, 30. That equals 0.5 mv squared. Let's crunch the left. Oh, I can do this in my head because 3,000 times 3 is 9,000 minus 6,000. Is it 3,000? Double check me. But I think the left side works out to 3,000. Yeah? So we get this. 3,000 equals 0.5 m the final squared. Is that right or am I wrong? Is it not 3,000? Right? 3,000 times 3 minus 200 times 30. Boom. Now let's get the v by itself. Where? Here? Except I said, isn't that mg? So why would I could divide by 9.8, but you know what I'd do next? Times by 9.8 for this specific one here. Because I didn't plug in m, I plugged in mg. I got lazy. But we'll have to do that for this m? Yes. By the way then, Cleo, how would I get the v by itself? Divide by 0.5 m? V final is going to be 3,000 divided by 0.5, and m is 3,000 over 9.8 square root. There's the m. Cleo, have you noticed I have a kind of a lazy streak? I would probably go like this. I would probably go 3,000 divided by 9.8 equals, I would just store that on my calculator. There's M. And now I would go 3,000 divided by bracket 0.5 times M, answer button. Square root of that. Oh, this might work out nice. Nope, never mind. It worked out nice inside the square root. That was a nice fluke. 4.43. To do that with forces would have been, no pun intended, way more work. Could have done it. It was much better to use energy, G. What's your homework? Oh, no, I got one more, sorry. Oh, I got a short video to show you. Okay. I think this is the last one. Okay. Roller coaster. A says, if the ramp is frictionless, write a work energy equation and find the speed of the roller coaster at the bottom of the ramp. Okay. What's this question want me to find, Sean? Speed. Speed or velocity? There's a reason I said speed. I'm hinting at you, use a scalar approach. Don't try using kinematics and velocity. Scalar. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? You know what this is a job for? Conservation of energy. Okay? You're getting fidgety. We're on the last one. We can do it. I'm going to start writing right here. It's going to be KE initial plus PE initial equals KE final plus PE final. Does A mention that it wants us to include friction and heat? Oh, cool. Oh, you know what? I glanced at B. B wants me to include friction and heat. Okay. Are any of these zero? Ground. A half mv initial squared plus mg h initial equals a half mv final squared. Oh, Josh, is there an m in the first term? Is there an m in the middle term? Is there an m in the last term? Is there an m in everything? Have you gone on a roller coaster before, Josh? Before you got on the roller coaster, did they make you stand on a scale? Did they measure your mass? Did they have to balance everybody out evenly? They did? No. No. Do you know why they didn't have to, Josh? What cancels? Darn right. And by the way, in other words, if you make the car twice as heavy, it's not going twice as fast at the bottom. Doesn't make any difference. What are you trying to find? I'm going to be clever. I'm going to go times by 2, times by 2, times by 2. Multiply everything by 2. Don't forget to multiply the middle term by 2, because equation solving says you have to multiply everything by 2. But when I do that, Allie, I get a much nicer equation. I get VI squared plus 2GHI equals VF squared. VF what? VF what? So? You're getting tired and we've written a lot. Let's try going to our calculator without even writing out the numbers. On a test, you would write out the numbers. Here, looks like VI is 2 from the picture. Plus 2 times 9.8, not negative because we're in Scalarville, times 10. Square root of 200. Oh, I can do that in my head. 14.14 something. It's the square root of 100 times the square root of 2. So it's 10 times the square root of 2. And I happen to know that the square root of 2 is 1.414. So times 10, right? 14.14, 14.1. Now, Josh, in real life, there is always some friction on a roller coaster. Do they grease those coasters down pretty good? Yes. If you were actually analyzing, say, a Playland roller coaster, this is your theoretical value, you'd be pretty close to the actual value. The actual value would probably be 13.8, 13.6. You'd be close because they grease them down pretty good.
Is there like any kind of difference if there's like one of those blue things?
Yes and no. Energy is still conserved, but I hope to, when we look at circular motion, I hope to actually analyze a roller coaster loop. Okay? While you're in the loop, because you're moving in a circle, our rules are going to change. The next unit after this is circular acceleration, and you're going to get yet another equation for acceleration. B says if the speed is 12, not 14. Oh, what were we supposed to get as an answer? 14.1. When we measured it, what did we actually get? Oh, before you go, Nick, can I give you the homework questions? Sure. We must have lost a tiny bit. Oh, by the way, water slides, also great examples of conservation of energy. The only issue there is you give up a lot of your energy to pushing the water. Okay? Otherwise, you would shoot out the bottom at the same speed as you would hit the ground if you jumped off the water slide. That doesn't quite happen. So, but still, they're still nice examples of conservation of energy. It's just you run into water resistance instead of air resistance. Eventually, you're going fast enough that you're just pushing water in front of you. Yes? I suspect there might be an issue on some of the corners where they've had a bad experience somewhere in North America where someone flew over and off one of the corners. Maybe. You need to find me the specific example of the specific slide. Or it could be a structural issue where they're going to say, we're having 4 people on this slide at a time as we let people go on, and this slide isn't built structurally to handle more than that. So the M cancels when we're talking about energy, but never cancels when we're talking about infrastructure. You know, a big truck, even though energy is conserved, a semi-truck can't drive over a little rickety wooden bridge because they're in the forces equations, M's not going to cancel. B, I think it's going to look like this. KE initial plus PE initial equals KE final plus heat. Why didn't I bother writing PE final? What's my final potential energy if I'm on the ground? I actually looked up here. Oh, I cancel. It's going to cancel there too. Okay. Marcus, what are they asking me to find in B? Not friction. Close. Read a few words before friction. Energy, heat. Okay. Friction's a force, heat's the energy. The work done by friction, if you want to be poetic. How would I get the heat by itself? This is the other one where for some reason kids divide, and I don't know why. Yeah, it's just going to be KE initial plus PE initial minus KE final. That equals your heat. KE initial is a half mv initial squared plus PE initial is mgh initial minus a half mv final squared. Josh, is there an m in the last term? Is there an m in the middle terms? Is there an m in heat? So do the masses cancel this time? But if we grease this coaster down, we can reduce heat to near zero. And so I've fibbed to you a little bit. In real life on a coaster, the masses don't exactly cancel, but close enough that an empty coaster and a full coaster can make it through. That's close. Let's go straight to numbers. because you guys are zoning out and I've been talking for an awfully long time. 0.5 times, what was M? Did they tell me M?
No.
Sorry? Oh, 1,000? Times, what was VI? 2, don't forget the squared. Plus 1,000 times 9.8 times, was H 10? Minus 0.5 times 1,000 times, in part B, what did they say that V final was? 12 squared. How much energy was lost to heat due to friction? 28,000? Or I could be wrong. If not, go check for typos. 0.5 times 1,000 times 2 squared plus 1,000 times 9.8 times 10 minus 0.5 times 1,000 times 12 squared. Am I right? Is it 28,000? Connor's wrong? Should have assumed that. Units, it's energy. What are the units for energy? Joules. Okay. Wes, you gotta lift your head up. Stay with me a little longer here. Let's look at the homework. Number 1, take a look at it, please. It says calculate the potential energy, the kinetic energy, mechanical energy, that's a synonym for total energy, at various locations. So, if I look at this, what's their initial potential energy at location 1? Be obvious. What's their kinetic energy? How would I calculate the kinetic energy? Could you please? Could you please? What do you get? 1940? 1920? Is that right, folks? Yes? So what's the total mechanical energy? Is that right or not?
Yeah.
Yes? Okay. So what's the total mechanical energy that we're starting with? What's the total mechanical energy that we're going to have everywhere through this question, because energy is conserved? So this is going to be 1920. This is going to be 1920. What's your question, Allie? You're looking puzzled. Half mv squared? Yes? Here's m, here's v, half mv squared? Yeah. Okay. Right here, what's the height? Could you calculate how much potential energy by going mgh? And if you're starting with 1920, would that tell you how much was left for kinetic? And if you knew the kinetic, could you figure out v? Yes. So try number 1. Okay. Answers are there. Number 2 is really similar to number 1, but it's a roller coaster. Hey, Wes, look at number 2. Is there a loop? Answering your question. Okay. Number 3 is good. 4 is good. Clearly, we're skipping 6. 7 is good. Skip 8. Trying to think about how much I've covered with you. 11 is good. 14. And then I'm going to start to give you homework from the ultimate review. So from the ultimate review, you can already do the following questions. Let me get a copy and then I'll tell you. Ultimate review, Noah, you found it this time? Oh, sorry, that slipped out. Could you circle question 3? Question 6. 8. $10. 12. 13. Roller coaster. 20. Skipped a bunch. 22. We'll pause there.